So the transactions using DMA are peripheral to memory, as I explained. Memory to peripheral. It could be that processor wants some data to be written into the peripheral, so that can also be given off to the DMA, and DMA can initiate. So processor will keep some data in the memory, and then it will ask the DMA to take care of writing into the peripheral. Or it could happen from memory to memory, because there could be a ROM, one part of the memory, which is where the ROM is, EEPROM or ROM flash, and then that needs to be copied into RAM before the data is before the code is running, or maybe the data portion has to be written from the code image, as I explained in the previous lecture. So data has to come to the RAM from the flash initialized data. So those kind of things can be done by memory to memory copy. So this will be mapped to some physical memory, and this will be in a different memory area, physical memory area, and the copying happens from memory to memory. So all these transactions can happen. Data can be quickly moved to by DMA without any CPU action. This keeps CPU resources free of for other operations. Dual AHP master bus architecture, one dedicated to memory accesses and one dedicated to peripheral accesses. So there are some these dual master architecture where one is dedicated to the peripheral part and then other one is dedicated to the memory. So because mostly what you see in the system is the data transfer between memory to peripheral. Okay, so that can be performed by using DMA. AHP slave programming interface supporting only 32-bit accesses. So for the DMA, we need to configure it, right? As I mentioned that we have to give the start address and then what is the length of the transfer. Those kind of information is written into the DMA, okay, into some registers using a slave programming interface supporting 32-bit accesses. So during that time, while configuring the DMA, while programming the DMA behaves like a slave from the ARM perspective. So ARM is a master, maybe a ARM or any other processor who is initiating a DMA transfer will be a master, and DMA will be a slave. So it is writing into it saying that this is the starting address and this is the length of the data. And then what happens once this is done, when the DMA it starts off interacting between memory and peripheral and then performing a transfer, the peripheral data comes to the DMA and then goes there. Okay, it could be cannot be written directly, but there may be a transaction happening initiated by DMA between memory and the peripheral. So that during this time, DMA behaves like a master because that is what is controlling this first transaction. So DMA takes a dual role. One is it behaves like a slave when it gets programmed, and then it behaves like a master when it has to perform the job done by the processor by writing into its own register. Okay, and 8 streams for each DMA controller. So there could be a multiple DMA controller. Okay, and there can be multiple streams, and within each stream there can be multiple channels. Okay, so it's whatever I explained is for only one transaction, but there can be multiple transactions programmed, and then they can all be happening in parallel because the AHP bus is very high performance bus, and the devices that it is normally interacting with are all slower devices. In this case, even slower devices, it may take some time for making the data ready. In that, it both means the same, but the slow devices means the data rate expected from the device may be less. Whereas there may be some memory to memory transfer where it may not be slow, but the time taken to set up the thing may take little more time. So during that time, what happens? The bus can be multiplexed. It could be used by some other transaction. So the DMA can be programmed for 8 streams, and then within each stream 8 channels could be programmed. Okay, so this is a generic block diagram of the DMA. Okay, so there is so within the DMA there is an arbiter. This arbiter is different from the arbiter that we saw at the AHP bus level. Okay, AHP bus level there is an arbiter which decides who is the master for a particular transaction. Okay, so choosing that is done by an arbiter on AHP bus. Within the DMA, because there are multiple channels and multiple streams are there, we need a arbiter inside. So there may be so many requests from each channel coming in, and one of the channel selection is happening, and then that request goes, and then the transaction happens. So the memory port, one master AHP port is connected to memory, and the other one is connected to the peripheral. So what does it mean? Actually, this particular port could be a master on the AHP bus. That's what I'm saying. Master 1, master 2. So the DNA controller itself gives the two masters on the AHP bus. Behaves like a two masters. So that means they can each of them can compete for the bus access independently, though it is from the same controller. So it could be for a much different stream. The transaction may be happening between memory to peripheral or memory to memory. So it could behave like a two masters, and then while programming it behaves like a slave. When it gets programmed, it behaves like a slave. So there could be some already programmed and the transaction is happening through this code, and then another DNA channel gets programmed through the slave code. So all this can happen in parallel. So this I have taken it from ST microelectronics reference manual. This is one of the implementation of the DMA block on the ARM AHP bus. Okay, so as I told you, the data has to flow through the DMA. So when peripheral device is giving some data, it has to be copied to the memory. It comes into the DMA, okay, and then goes to the memory. This is the memory. So this is the path taken by the data flowing from peripheral to memory. So that way the DMA has a FIFO. It normally is a 4-word depth, 4-word depth of FIFO. So it gets written into this, and then a bus transfer happens to the other side. So these transactions can happen in parallel. So the data could be written by either any of the streams. It could be read by any of the streams. So it comes into the FIFO for the data. It reads as a block of data, and or it accumulates the data here in the FIFO. So as then there are some peripheral device like UAR or no serial device may give a byte-wise data. So it has to accumulate to this way. In that case, if a value, a nibble is A, suppose, what happens is it will be converted into BCD form, okay, occupying two nibbles. This will be 0 and this will be 1. So effectively A will become the 1 0. So this A segment display can show this information. Not an issue. Suppose we have a C, which will be occupying a nibble value of 8 plus 4, right? C. So this is the equivalent binary representation of C, but this will be shown as 12. So it will be in a BCD representation. This will be actually 12. So it will have 0, 0, 1, 0, and then this will be 0, 0, 0, 1, and then okay, it will be transferred to the display. So that kind of a BCD counters are required because the time when it is displayed on the screen, we want to see it as 10 on 10, 10 hours and 10 minutes. We want to show the time in this format, not like A colon A, so that nobody will be able to comprehend it. So that's the reason, human readable form. So RTC provides time of the day clock or a calendar, two programmable alarm interrupts, and a periodic programmable wake up flag. So can be multiple, but it can be alarm interrupt. That means what? You can set up an alarm, say that you wake up or given interrupt after this time period, or after this time is elapsed. Suppose when it is time is 5 o'clock in the morning, generate an interrupt, so that it will, ISR will be called, and then that will set an alarm, and then you will wake up at 5 in the morning. I don't know whether you want to really set it up at 5, but it will be good for you to review or read up architecture at this time. Okay, it will be good auspicious time. Maybe you can try for 4 a.m. after being successful at 5. So you can set up a programmable alarm interrupts, periodic programmable wake up flag with the interrupt capability. So you can even enable interrupt. So RTC also includes an automatic wake up unit to manage low power modes. So as I told you, the ARM processor SoCs, ARM-based SoCs are meant for embedded systems. What happens when there is no activity from the environment? Okay, there is no signal or nothing is happening. It is like you might have noticed when the laptop is, you go out for 10 minutes, you come back, maybe based on the configuration, you would have seen that the display is blank, and then after some time maybe it would have shut off the processor also, and then it will be sleeping. So how does it happen? How does it know that you are not sitting in front of the computer? Because there is no keyboard entry, there is no mouse movement. Okay, keyboard is not touch, and then there is no mouse movement. Okay, so once it doesn't see that any of these two things are not happening, there is no scrolling of the display, and then the first display dies, and then later on then maybe the whatever is there in the DRAM will be copied into the disk, and then the whole processor shuts off. So all these events are happening based on some time. How it will be counting the seconds, or how much of time has elapsed since last input was received from the keyboard or a mouse. So these kind of things can be programmed using this kind of a RTC wake up unit. So once we set up and then it goes to sleep, it has to come back when you come back to the PC and then move the mouse. Then what happens? Initially the mouse driver may be active, so it may wake up the rest of the software, the rest of the OS, and then there will be resident OS. Some part of the code will be running, and then the power to some of the other modules or peripherals will be shut off, so that the other peripherals do not consume power. Maybe monitor will be switched off, in the sense it won't be powering the monitor, but the data which is going to be shown on the screen may be in the graphics processor, and it will be stored. So this is a kind of a PC environment I am talking about, but in the embedded world also we can do that by shutting off the modules. As the time progresses, that there are no activities or no signals coming from external world, then it can go to sleep mode so that it saves power. Especially your mobile or tablet, they need to do this to save power. So we have provisions in RTC to go to sleep as well as wake up on different, when the events are noticed. So 2 32-bit registers contain the following expressed in BCD format. So I am showing some examples, but it may not be only 2, it could be anything. So it could be for showing this format, and then day of the week, day of the month, and then year. So subsequent values also available in binary format. So these are all in BCD format because we want to show it in this to the outside world, but other data could be in binary form. So this is what is happening in the real-time clock. Now compensation for even the leap year is implemented in the hardware. Daylight saving. So in the US or in Europe, you always see that the clock gets shifted by 1 hour, okay, or shifted back by 1 hour based on whether it's summer or winter. So these kind of changes happens on a particular method number some time, okay, within a during a particular time in the calendar, day of the calendar. So once the calendar shows that this is the time, then when that 12 midnight happens, it can automatically do this, because it is very important for embedded system to be aware of this daylight saving, because the system may be in a flight, okay, so it could be in a flight, so it needs to be aware of the changes, otherwise you will have dangerous ramifications if the time is not adjusted accordingly, okay. So additional 32-bit registers contain the programmable alarm sub-seconds and second minutes hours day. A digital calibration feature may be available to compensate for any deviation in crystal oscillator phase. So that is another thing. Because of the temperature or because of a shear material degeneration, the crystal oscillator may oscillate. So because of that, the accuracy of the basic time tick measured by the processor will be affected. So there will be a compensation for that built into the system. So as long as the supply voltage remains in the operating range, the RTC never stops regardless of the device status. That is very important. So if you have seen in the motherboard also, there is a button battery will be there to make the RTC run in our PC. So even if a battery is down, laptop battery is down, and you are not connected to the power and it is shut down for a long time, still the RTC will be running because of a small battery that is there in the motherboard. So the basic clock has to be running, because we have to keep track of the date and time of the calendar. Okay, how long does the device has been down. So when you bring up the OS again, you have never seen that the time and the calendar changed because of the RTC running continuously. So it could be in a run mode or power mode or under reset. There are more different device status are possible. Then what are the other features? Daylight saving compensation, I told you already. 2 programmable alarms can be there. Alarms can be triggered by any combination of the calendar field. So you can say that if it is a Saturday or if it is a holiday, okay, maybe if you are scheduling an event or particular time, then it has to pop up a window to say that message alert has to come saying that, hey, you are supposed to meet so and so at this time. It's already 4 o'clock, so please carry on. So this kind of how does it wake up? Because based on the calendar event. So what is the current time or calendar time, date and time, and then the event, calendar event what you have mentioned, it will compare these two and then set up an alarm or alert, message alert, so that the pop-up window comes up on your screen to alert you. Automatic wake up unit generating periodic flag that triggers an automatic wake up interrupt. So you may want to set up an alarm, or you want to set up a periodic interrupt. So those kind of things can be there. You can connect to the interrupt. Timestamp functions for event saving. So sometimes when you are maybe heard about the data recorder, okay, in the flight, what you see as a black box. So it has to record the information about all the flight details periodically. So it has to log that information. Okay, what are the different sensors, engine temperature and their RPM and their speed and their inside temperature, outside temperature, whatever, or pressure, cabin pressure, tire pressure, whatever it is, whatever is needed, and then cockpit dialogue. There's so much of information needs to be saved, and those functions and some events have to be timestamped. So when particular event has happened, suppose if any anomaly is found or any particular event has happened, engine speed has crossed some threshold or some brake, liquid, in the maybe hydraulic braking system as a liquid pressure is, maybe a leakage. Then if the pressure in the hydraulic braking system has come below a threshold, then what time it has happened, what event has happened. So all this time stamping of those events needs to be done. So that is possible. And then even for debugging purpose, you may have to timestamp some event. So that all is possible in the object. What are the applications? It could be done in a switches or servers, because whatever I have shown you, gave you us all embedded systems. But even the router, when it there is a big network traffic, because of network traffic there is a clog. Maybe a particular path is completely swamped with lots of DOS or attacks. In that case, what happens is maybe the router has to find another route for a, based on the traffic and congestion, it has to find another route. So, and it has to register the event also when the congestion has happened in a particular route, so that it can the network management management can get the log of all the information. Then they can take corrective action, maybe introduce another high speed link, so that this congestion can be removed, or they may even see that the particular time when this congestion happens, then they can configure the network accordingly. So all this can be done with a RTC is supported there. So handheld, all these devices have RTC support. Set-top box and digital recording. Maybe you may say that you want to record a particular program which is starting at 7 p.m. So, and it should record for 1 hour. So this you can set it up in the set-top box and it records it. It opens, it connects with the home network attached storage, NAS, and then it copies, TV program, whatever is coming into the cable, that can be copied into the NAS. So it generates a file at a particular time, and then it shows that particular program saved in it. So you can come home and watch that later. So for this we need a RTC, otherwise we can't do this. So it could be printers or copiers, they also need RTC support. And especially very important, these kind of medicine dispensers will be programmed for a particular delivery of medicine, so that needs to be programmed. So there are so many devices like this which need to be aware of RTC. So whenever you take photos, you will see that on the down photo date when it was taken with it along with time. So you want to know the time when, date and time when you took the particular snap. So all this is possible because of this RTC support. Okay, in the system. Now let us get into another world of the digital converter. I will let you know. You may be aware of all this. Let's go too fast. So the signals in the real world are analog, all of you know, and real world signals are converted into digital form before they can be manipulated. So who does that? Analog to digital converter does it. So what are the examples? Scanning a picture using a scanner, recording a music or voice using a PC. Even the lecture that you are hearing now is done by an ADC. By whatever I speak is getting converted into the digital information and then saved along with this. Whatever you see, even whatever I draw here is getting converted into digital form and then saved for that to be reproduced later. So voice call, you might have used Skype, and whatever you speak, and if your video call, then your image, everything is converted into digital and sent over the IP packet. So it's all done in digital. Hearing your audio CD on a PC, or playing a DVD, viewing using set-top box, anything is done by audio, with the help of ADC. So basically, the input or the signals are generated in the audio world, and then the microphone, whatever it converts your speech or the music, it actually generates a pressure difference, and then on the microphone it generates an audio signal like this. But finally, when it gets converted into an MP3 file or audio file, some other format, they need to be stored in a digital form. So this analog signal is converted into digital world for that to be represented in a different format and compressed and then stored or sent over the network. So that is done by the component ADC. So consider analog audio signal above. Let us assume that it is an audio signal. Okay, y-axis represents a voltage. So this could be this is typically an voltage, but it could be a different sensor. Pressure sensor, maybe it may be a pressure. But generally the signals are generated in terms of voltage or current. Okay, that amplitude of that. It need not be only voltage; it could be a current, and then that is the electron is converted into V voltage and current can be changed from one from the other, and then it is sampled. Okay, at a particular instant. and then the value is converted into some digital form for it will be a 12-bit word or a 8-bit word, and then it is stored as a digital number. So the voltages are in y-axis and time is in x-axis. So ADC takes samples from analog signal periodically. So it has to be periodical. Okay, you can't take one here and then one there, and then you can't reproduce the signal. So you should take it such a way that you get every not all the changes, but at least most of the changes, so that we can easily grab the finally plot the signal more or less closer to this signal, whatever you have seen. Okay, so the digital information is only stored, and then later on it is reconstructed to form this particular analog signal later on when it has to be reproduced at the while playing this audio. So frequency of sampling is called sampling rate. Each sample is converted into number based on the voltage level. So you may convert it into 8-bit voltage level or 16-bit voltage level. So which one? No, this is 8-bit and this is 16-bit. Then you will know that this has got higher resolution, because we can define. Suppose if you limit this to maybe this is plus 2 volts and then this is minus 1 volt. We normally the dynamic range may be we assume that it is plus 5 to minus 5 volts, because you just based on this signal you cannot say that this is the dynamic range. It could be more than that. So if this is the dynamic range of the signal, then this can be mapped onto 0 to maybe suppose 8-bit. It will be FF, correct? Then based on this, it could be maybe mapping to some 20 hex, and then this may be mapped onto some A0. Okay, like this you will be converting every value into a digital decimal value and then storing it in as a 8-bit pattern, and it will be done in sequence. Now if you are taking 10 samples, it will be sequence from 0 to 10. All will be generating an 8-bit value coming out. So this is what is a sampling. This is called the frequency of looking at the audio input or any analog signal is called sampling rate. It's also sampling, and the speed with which you do is a sampling rate. Now there is a generic theorem which most of you, if you have taken communication or even EC background or electrical background, you may be aware of this, but just for a continuity sake, I thought I will mention it. A bandwidth limited signal. What I mean by bandwidth limited is that the change in the frequency of the signal is limited. Suppose if in an audio signal, human voice can go up to maybe 0 to 20 kilohertz. So even if you scream through your high pitch, whatever you try, you cannot generate more than the 20 hertz signal. Okay, so 20 hertz will be more than this, like this, and then maybe 1 hertz will be smaller. So whatever it is, if you need to sample this, you need to sample it more than this rate. Otherwise, you will miss out on the data. So we should first of all know what is the frequency band of the particular signal that we are sampling. So then only we can decide the sampling rate. So bandwidth signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency. See, once I say that our speech can have 0 to 20 kilohertz, you will not be always screaming at this frequency. Maybe you will speak mostly here. Maybe if you are hearing a song or something, or even most speech song, maybe you will have audio instruments coming into play. But human voice, if you are only singing, somebody is singing or you are singing, then sometimes it may reach this high pitch. Okay, the high frequency band of the signal. So but we need to cater for the maximum frequency that might be generated in a speech signal. So if it happens to be 20 kilohertz, then we have to sample this at a 40 kilohertz. That means we may have to generate signal every 1 by 40 or 1 by 40 into 10 power minus 3 is 1 by 40 milliseconds. Okay, so every 1 by 40 millisecond the sampling has to be done, because we don't know whether a particular point in time whether the signal generated is at this maximum range or not, at this range or not. So we may have to do it twice the maximum frequency. This is what is the called Shannon's Nyquist criteria. That is, the sampling frequency should be at least, okay, it should be greater than or equal to 2 FM. FM is the maximum frequency component of the message. Okay, so I hope what I gave and this theorem, you are able to understand it. Okay. So ADC parameter, the value of each sampled point is stored in a fixed length variable. If the variable is of 8 bits, then you may have 255 values, 0 to 255 values, or 0 to 65K. So ADC divides the y-axis into n possible parts. As I told you, 0 to 255, it divides the dynamic range of the signal into this many parts. Okay, this is called dynamic range. And then the n is given by the variable size, and n, if higher n, better resolution or quality of the sampled output. So your output will be more closer to actual value. See, whatever you do, the actual analog signal will not be stored as a digital form. But if you want it to be closer as much as possible, then you may have to have a more resolution. Okay, in that case, the error will be the plus or minus something will be there. Okay. So, but more storage space is needed. But if you increase the width of the sample, then you need more space. So, if you are 1 hour recording of an MP3 file as well as with a higher quality, that's why you will say that whenever you are saving some video, it will say high quality or low quality or medium quality. So, based on the quality, you may have to sacrifice on the storage space for storing the value. That is after the ADC out, analog to digital conversion is done. In summary, the sampling rate corresponds to x-axis and the resolution, and the variable sizes represent the y-axis resolution. Okay. So now let us see what is inside an ADC. So ADC takes the voltage input and then generates the digital data. The n is the width of the data which is coming out. So I have taken, I referred this particular link below. And you can have a flash ADC. That is, if we are electronics background, you will be able to appreciate this. But still, I will explain you. Assume that there is a voltage source which is called V reference. Please remember, this need not be same as the operating voltage of its IC. So normally now we are trying to build ICs which are operating at a lower voltages, maybe 2 volts or 1 volt or even it was earlier 5 volts and it has come down drastically because we want the low power devices, means the voltage sources also is coming down in terms of value. But as far as ADC is concerned, there is a separate voltage source given, and which happens to be a more stable reference, which is called a V reference voltage. I will talk about this in the next slide. Assuming that there is a resistor ladder like this, and then you have maybe a fixed values, then a simple example is, suppose I have 2 resistors. Okay, this is ground, and then I am giving 5 volts. Okay, and assuming that this is 1K, or I will think for an easy calculation, 0.5. Okay, 500 ohms. This is 500 ohms. Okay, this is very not practical. If you are putting a 500 ohms for 5 volts, better the high wattage resistor is put here, otherwise you will blow up the circuit. So 1K. So what is the current flowing through this? Okay, simple current is V by R. So 5 by 1K, correct? 500 plus 500. So it will be 5 milliamp, correct? So what I am saying is, this is split into 2 voltages. So 2.5 volts come here, another 2.5 volts have to come here. Okay, because it is an equal resistance and it will divide the voltage equally. So if suppose I have put only 2 ladder like this, and then a voltage comparator, okay, like this. This is a comparator, and then I am giving an input voltage something like 2 volts. Then this is closer to this. Okay, it will give an indication that it is between this 2 and 2.5 volts. So any 2 volts or below will say that this is the output. Okay, it will generate a particular output, maybe 1 or 0. It will generate 0, and if it is above, it will generate 1. So based on the voltage, okay, we need to take a sample in 2 places. Okay, maybe this is only one place. Maybe I have to give one more resistor so that I will have one more sample taken, so that I will have a range of values. In that case, you may have to divide this further. So you can, basically you can understand that if I put more resistors here and dividing this 10 volts is there and 10 resistors are there, maybe same value, then I may be dividing it into 1 volt each, and then I will give a range of values 0 to 1 volts if it is an input, then it will generate from 00 to 111. So it may generate some values. Okay, it will be coded like this, and then 1 to 2 may be 001. So like this we can generate based on the value which is coming, and then what comparator fire. So all of them will not fire, only one of them, because the voltage given will be matching with one of the values, because you are dividing the reference voltage into multiple data points. Okay, samples, and then this will be equated to one of these values in the ladder here. Okay, I hope little bit easy value will be able to understand, but I hope this explanation is clear enough. So basically this is, as soon as the voltage comes here, and then if sampling needs to be done, okay, then the digital output is ready. Okay, this is one way of doing it, very easy. Another, what is VREF? The voltage reference provides an accurate and stable point for ADC and DAC for data conversion. The voltage reference and can be fixed with different levels of voltage accuracy and temperature stability. So we can fix different levels of voltage accuracy based on the resistors or what circuit we put. Normally, okay, the V reference that we need to put. Normally, a power supply will fluctuate with current drawn. Okay, normally you see that even in our home when we load the we switch on all the you switch on the AC or TV, everything, then you see that the light goes down in terms of brightness. So as the current drawn increases, the voltage will be fluctuating. But this V reference is supposed to be irrespective of the current drawn, it will maintain the voltage source, that's ideal voltage source. So power supplies are usually designed to be plus or minus 5 accurate normally, but in this case it is plus or minus 1% accurate. So if you say that the V reference is 5 volts, you will never be seeing a voltage which is going beyond this 1% range. So another implementation is DAC based. So it's very simple. What is done is the V in voltage comes here and a comparator is there. What is the counter? There is a counter which is starting from 0 to some max value. Okay. So this max value will correspond to the maximum expected voltage from here. So V max. But it will give out values from 0 to V max. Okay, maybe 0 volt. Okay, to V max in some particular steps. This value. So whenever the input voltage is closer to one of them, then it will fire. This output will be controlling it, and it will stop the counter. Then that is what is the converted value. That is the wherever the counter stops is the actual converted value of the voltage source. So we are using a DAC inside a for implementing a ADC. This is what is very interesting. So we use a DAC. I will talk about DAC, how it is implemented. But what is done is counter is made to run whenever sampling has to be done. The counter is made to run from some 0 to some FF based on the size of this. If it is 8 bit, 12 bit maybe we will have maybe 3 Fs. Okay. So it will go from one to the other, and then each of these values will correspond to some voltages from 0 to V max. It will be exactly split into equal parts. So whichever voltage that comes across, which happens to be same as at that time whatever is the current voltage, then the counter is stopped, and the counter value will be the converted decimal representation of the input signal. Okay, I hope this is clear. So we will be starting the counter and ending the counter, and there will be a clock to how fast this particular counter runs. The main problem with this circuit is that it is very slow, because it has to every time whenever it has to sample, it has to run the counter from 0 to the maximum value. So it would require 2 power n minus 1 clock, because the maximum, if there are n bits, there will be 0 to 2 power n minus 1 possible values that could counter take, and counter takes 1 clock to increment from one to the other. So that many clocks it will take for the counter to count from 0 to 2 power n minus 1. Okay, so it is slow converting any given value to a particular voltage. Okay, fine. This is, I hope this is understandable. So these are different methods of implementing the ADC. This is another successive approximation. This is what is normally implemented in any of your ADC what you see, but there may be some advancement the basic functionality. But here what is happening is the values are actually chosen. Okay, it's like a binary search. It is trying to, instead of blindly going from 0 to FF, it will put some value which is in the middle. Okay, 180. Okay, this is the middle value, and then it will check whether the value whatever is input given is above this or below this. If it is above this, that means what, this is a smaller voltage than this particular voltage what this A0 represents. A0 represents. In that case, what happens? It will maybe give another one. It will be 0 1, that is 4 0. So it will be middle of this, and then 2 0. Okay, like this it will be go on. Sorry, okay. So actually you can convert quickly based on this, successfully approximating the value what is coming based on the result. So suppose if this is more or less than this particular value, the count will be this value what is generated, the counter will be varying based on the value which is there. So this is called successful approximation. Advantage of this method is speed. At worst case, it will find the correct digital value sample at n clock cycles. N is the number of bits used. So worst case, it will be maybe fluctuating. Because of that, you may have a problem. It is not exactly a binary search, because when you are looking at the voltage source, it may be in a border case where you may not be able to exactly find where it is. So you may have to do the maximum of n clock cycles. If it is 8 bit, it will take maximum 8 clock cycles to finally converge onto the value which is closer to the input voltage. So this is how it is implemented. This method is most used one. So ADC features, it could be a 12 bit or 10 bit or 8 bit or 16 bit configurable regulation. That is n. Okay, and then interrupt generation at the end of conversion, single and continuous conversion modes. So after the conversion is done, after the sampling is done, it can generate an interrupt. Stand mode for automatic conversion of channel 0 to n. So you may have multiple channels with the analog signal with the various sensors are connected. Then ADC will have multiple channels. So it will be converting this first and then next this, next this, next this. It can go into a particular order by sampling the values of different inputs. So periodically, if you want to sense different parameters, all the sensors connected to the system, we can periodically, the ADC can be sampling all of them and then getting the value and generating a digital information about that. So data element with inbuilt data coherency. It could be a 8 bit aligned, or 12 bit means it has to be aligned internally. You have to 12 bit, how are we going to store it within a 32 bit register? Okay, because normally you see that our internal registers in ARM are 32 bit. So but the ADC outputs are not even close to 32, right? It is all sub 32. So how do we store it? So that is another thing. And then alignment, that is channel wise programmability, sampling time. Maybe you can say that some data is very fluctuating more, then you can sample it at a faster rate. Maybe this is a slower device, not a slower device, but the data which is coming out of the device is not fluctuating so much. So and it is not very important also that you can sample it at a slower rate. So you can decide a sampling rate based on the device and the importance and the kind of changes you expect on that particular device. So external trigger option with configurable polarity for both regular and injected conversion. Sometimes you may have to look at the data only when some particular event happens. Okay, so sampling is not done always. So suppose if there is a motor speed is 1, okay, and then sensing the temperature of the motor is another data. Suppose speed is exceeding some limit, then maybe it is better to look at the temperature to see whether it is exceeding the allowed threshold value. Okay, then you can control the speed, or you can coolant, maybe you can send more to cool down the motor. It can be some action can be taken, or you can inform the user that you are exceeding the allowed speed limit because the temperature is exceeding the thing, and maybe if it goes beyond some point, maybe switch off the motor forcibly. So all these things can be done only when you sample the data based on some event. So that is called injected conversion. So you have to sample the input based on some event. So some more features, discontinuous mode. So you don't have to sample it periodically, but at a in a discontinuous mode. You don't have to do it in a continuous fashion. So dual or triple mode, there are multiple ADCs can be there, and then they can be sampling the data. So there can be dual mode or triple mode. And another important thing is DNA storage on the ADC. So ADC is a peripheral, I said, and I told you also DNA can be connected between peripheral and the memory, correct? So now, if the peripheral supports a DNA option, then we can do that. Okay. So some of the most of the peripherals normally in the ADC support that. So we can do a DNA transfer. Configurable delay between conversions, that is also possible. Interleaved mode. So you can delay the sampling and then interleave sampling of two devices between each other. Configurable to control and status register. Mostly always any peripheral device will have a control register and a status register and maybe interrupt enable register. So you can enable and there is a device enable register. So enable it, and then interrupt could be enabled optionally, and then interrupt, and then we can configure it control register. Different modes can be set up. So then the device starts up. So similar to what we did at the MMU and MPU, we can configure the peripherals also like this using this. And these devices can be accessed using a typical memory map register of on the IIT bus or APB bus. Okay, mostly peripheral because it will be an APB bus. So that's all on ADC. Now let us quickly look at the DAC before we conclude discussion. So normally digital to analog conversion is similar to what we saw in the flash ADC. Okay, what is happening is there is a reference voltage. We want to convert a digital output to something analog. Okay, so the operating of these switches, it is based on the bit pattern. Okay, so that is what is controlling the switches. You can configure 8-bit means 00 to F at any value. So based on the value, if it is 1, maybe you may say that it is closed, or if it is 0, it is open. Whatever. Once you do that, you can close multiple things, switches. Maybe this and this are closed. So it will sample different voltage values based on which is connected, and then it will add up to that and then generate an output. Okay, so you can have 2 power n combinations of output coming out, analog outputs, because of you are adding up different voltage levels, and then that gets converted into what is given as an analog output. So this digital input is coming into the system, and then it operates the switches, and then analog output goes. So it is a DAC, digital analog, so conversion. This is a flow of data, okay, through that, and it could be done because these switches are done in one way, because so many changes here, there will be glitches on the output. So to avoid that, multi-level switches are there, and we can do that using this. Okay. So finally, the output what you get will be a stable output which reflects the values of these data bits. Okay, digital outputs. And then this, as I told you, that 12-bit aligned. Whenever you have a ADC or DAC output which is 12-bit, we have an option to choose the way how it is stored. So it could be in a 32-bit word, it could be written from 0 to 11. Okay, this is called right align. Okay, in 2 places. Okay, this is another one. This is 16 to 31, and this is 0 to 15 of a 32-bit register. We can have 2 samples written into it. Okay, both are aligned to the right side of the 16-bit word. So we don't want to store only one 12-bit word in a 32-bit register. Okay, 12-bit word. So it takes only this much time. 16. This is 16, and then this is another 16. Okay, another 12-bit is stored. So this is right aligned because it's aligned to the right side of the half words of 32-bit. Okay, so this can be configured. Similarly, it could be left aligned. So when I show the 32-bit value, This is 32 bit, this is 12 bit, this is another 12 bit. Maybe let me closely give. This is 16 bit and this is 16 bit. This is LSB and this is MSB. MSB, okay. This is bit 0, this is 31. See, the samples are here and here. It is left side aligned. Okay, both are. So these are two different ways of storing. And then DAC features multiple DAC converters with one output channel each, and then left or right aligned at 12-bit mode. Synchronized update capability. So we can update the data which is given by different DAC outputs in a synchronized way. Noise free generation. So there are so many general use case scenarios where you want to generate noise and then test your system under noise conditions how your serial port is functioning, or your encryption data, or what kind of error correction code that is implemented, how effective it is in the presence of noise. If you want to do that, you want to inject the noise into the system. That could be done in a digital world because you know that no analog signal is converted between using this to digital world. So you can introduce a noise with a signal and then see how the receiver receives it at the receiving end. Okay. So then it is equivalent to introducing a noise in the channel. So there are so many ways communication channels are tested using this. Even a triangular wave generation is possible. This is a triangular wave. Okay. And then dual DAC channel for independent or simultaneous conversions. You can do independent simultaneous conversions also. And DNA capability similar to what I said in ADC. And underrun error detection. So there could be possibility that the signal goes below the threshold values. External triggers for conversion. So some event happens and then you do a DAC. Input voltage reference could be DAC. Okay. So this is about DAC. So just small introduction about pulse width modulation. Because signal is a method for generating an analog signal using a digital source. So we want to generate analog signal using a digital source. How do we do that? So it could be a PWM signal consider two main components. So you can digital signal you can generate in so many ways. Okay. So this is called a cycle, and this is on and this is off. Okay. So the on time divided by total time, percentage is what the duty cycle is. Okay. Percentage of time it is on is called duty cycle. So if it is the very good square wave, the duty cycle will be 50%. Okay. Otherwise, if it is a smaller, then you will get a 25% and or less or more. So this is called a duty cycle. And then how frequent the signal is coming. What is the time? You can have a same 50% duty cycle, but the time could be smaller. It could be a smaller pulse. But it is 50 cycles. 50%. But the time taken is much smaller than this. So the frequency decides this time, this particular time width, and then the duty cycle is how long you think that particular cycle time that particular clock is on. So this is what is the definition of these values. So duty cycle describes the amount of time the signal is on state percentage of total time. The frequency determines how fast the PWM completes the cycle. So pulse width modulation is something to generate based on the analog signal. You generate you change the duty cycle and the frequency of the signal, then there is what is called a pulse width modulation. Okay, the PWM is one of the peripherals that could be there as a part of the system. Therefore, how far it switches between high and low state. It is normally used for powering motors. Okay, if you want to give input signal to the power motor, then okay, PWM is a normal algorithm used to run the motor, how to power the motor. Okay, or maybe you can do an LED if you want to brightness, if you want to control in a linear way, you can do it using the PWM also. So it generates the signal in this way. So it is a modulation technique, conforms the width of the pulse, formally the pulse duration based on the modulated signal. Although this modulation technique can be used to encode information for transmission, okay, it is also possible for transmission encoding. Its main use is to allow the control of the power supply to electrical devices, especially to internal inertial loads such as motor. And then in addition, PWM is one of the two principal algorithms used in photovoltaic solar battery chargers. main advantage of PWM is that power loss in the switching device is very low. That means when you have a switch, okay, using a transistor, okay, what happens is either the transistor will be in a off mode or a on mode. Okay, so what happens during this time? Sorry, on is on or off. The power drawn by the circuitry is less or a zero in both the cases. Okay, in the based on the load. Okay, so PWM is that power loss in the switching device is very low because of this on and off mechanism used for the particular, because on off is this is on state and this is off state, so the power consumption is minimal in this case. PWM is used to certain communication systems where duty cycle is used to convey information. You can even use the duty cycle. Okay, this is one information, maybe this is another information. Okay, the frequency is same in both the cases, but the duty cycle is different. Okay, so you can even convey some information using this signal. Normally, timer modules are programmed to generate PWM signal. So how we are doing the PWM? Because we want a particular time this should be on and particular time it should be off. So timer can be running with a final clock, and then you want this counter is there. Then for this duration it will be kept on, and then the timer will be running for some more time, which will be little longer time based on this off time. Then it will be switched off. It will be kept in the off state for such a long time. So on or off, where switch can be kept in this low state or in this state based on the timer running. So there will be a timers used inside to implement the PWM signal dynamics. So I think this session was very useful to you. It's just a generic overview. The purpose is not to give you a complete information about everything under the sun. So the programming the peripherals in ARM, I am not talked in detail, but it is already been talked about this in using the APB bus, how to access a particular peripheral device, and then I have also told you that AHB slave configuration is used for configuring the devices mostly. If it is a DMA kind of a thing, but if it is a peripheral, it will be on APB slave. Okay, but it will be written. Still, if it is APB also, the APB bridge is considered to be a AHB slave. So please understand, even the peripherals are sitting on APB bus, and you want to configure the devices, it will be still be a AHB slave as far as the ARM is concerned, because APB bridge is considered to be an AHB slave, and then it is gets written into the peripheral. So this is how programming is done in ARM using this peripherals. And my intent was to give you an overview of the peripherals so that you understand in your system if these peripherals are there and you need to program them, or you need to design some of them, or you need to integrate a peripheral with the SOC that you are configuring it. You know what is done by the peripheral and how it has to be integrated. I hope this was useful to you. Talk to you in the next session, and have a nice day. Thank you very much for your attention. Bye bye.